Yeah, I will start the recording now. Good evening, everyone, and welcome to week three of tutorials on analog electronic circuits. So before we start the questions that I have, I will ask that have you guys gone through the week three of the course content, and do you guys have any doubt on the course content?
No, sir. Perfect. Everything is perfect.
Okay, so then we will go through some questions over here. So first we will try to find out quick looking in impedances. Let's try to practice the small signal structure. Try to practice some circuits with small signal structure and see that what is our understanding in that. So let's start with this. So let's say we won't worry about the biasing of these structures. Let's say there is some input over here.
Sir,
This
screen is
is
not visible, sir.
just a minute. Is it visible now?
Yes, sir.
So we will try to have some examples in order to practice small signal model that we have studied so far in the course. So first of all, let's say this is a structure, and we want to find out the looking in impedance R out over here. As let's say this is a transistor with a transconductance of Gm and output resistance of R0, and there is a resistance at the source of this transistor. Let's call it Rs. Okay, so we want to find out the looking in impedance from this thing. Let's call this R out. We want to find this R out. So now first of all, what we will do, we will form the small signal equivalent of this structure. So, what is the small signal equivalent of the MOSFET? We have
Current source. Yeah.
VG, VS, and then we have GM times VG minus VS. In parallel to that, we have this output resistance of R0. Okay. So, can you guys tell me where will the
Sir,
RS come?
source side, sir.
Source side over here,
Yes.
correct?
Yes.
And where we need to find the output resistance?
At drain terminal, sir. We need to find it out R0.
R0. So for finding the output and where is the input?
VG, sir.
VG.
For
So this is equal to
to
VA.
find to find out yes.
Yeah, to find out
Yeah, to
what?
find out R not we can apply test voltage across the drain voltage. Based on that also we can find.
Yeah, so we will apply a test voltage at the drain voltage. So let's call this VT. And what we will do with V in?
V in short circuit, sir.
Short circuit.
De-energize.
Okay. Okay. So this is the circuit. Now let's what is the voltage over here? Let's call this VT. What will be the current? Let's say this is I test. Now this I test will be the same current that flows through the source resistance Rs. Can you see this?
Yes, sir. Because current will divide it and here it will add it. So it will be 80 only.
Correct. So what is VT? I test can be written as Vs by Rs. Okay, and
Yes.
or in the other words, Vs is equal to I test times Rs. Okay, so what is this current now? What is
Yeah,
the current that is? Yeah,
GM VG minus ITRS, sir.
what is Vg,
Oh, VG is VN.
and what did we do with Vin?
Okay, VN we DN చేసిన sir.
Yeah, so
Okay, VG is 0.
0 minus It.
ITRS.
Okay, and what is the other current? This current,
VT minus VS by R naught, sir.
Vt minus what is Vs?
VS ITRS.
Itrs by R naught. Okay, did you get this?
Yes, sir.
Okay, perfect. So from here, if you try to calculate It, what do you get? If we rearrange this equation, we get It times GMRS plus 1 plus RS by R naught Rs by R naught is equal to Vt by R naught, correct? So Vt by It we get as Gm Rs R naught plus R naught plus Rs. Is this clear?
Yes, sir. We can take R naught, we can common or RS.
Or yeah, okay. So let's try to see how this equation works. So what we had over here is, so this is a transistor with a self gain of Gm times Ro. Self gain is its transconductance multiplied by its output resistance. So its self gain is equal to Gm times Ro. Okay. So now
Sir, small doubt, sir. That means
yeah,
self gain means without applying any voltage, sir.
self gain as in let's say so how does the concept of self gain comes out? Let's say this was connected like this. Okay. It is basically the maximum gain that you get from the transistor when it's in common source configuration. For example, it's connected like this, and at the top you have a current source with infinite output resistance. Okay.
Hmm.
Okay, so in this case, if the transconductance of the transistor is Gm and the output resistance is R naught, what will be the gain of this circuit?
Yeah, minus GM into R naught, sir.
Minus Gm into R naught. And
Yes.
moment we keep on applying load at this particular node, your gain keeps on reducing and reducing.
Hmm.
So Gm R naught is the maximum gain that you can get from a transistor when you have a common source configuration.
Hmm.
So this is called the self gain. Okay.
Yes, sir.
Okay. So we have a transistor with a self gain of GMRO, and let's say we had a small resistor RS. Okay. So looking in impedance would have been just RS. Okay. So on top of it, if we place this transconductor over here, then our looking in impedance becomes GMRO times Rs plus Ro plus Rs. Now the self gain will be a huge number. This you understand, right? Transistor is in saturation will have some high amount of gain. Correct?
Yes, sir.
Okay. So in this expression of the output resistance, we have three terms, right?
Yes, we have addition of source resistance as well. Product of.
Yeah, just a minute. So in this particular equation, we have three terms. Now, can you tell which will be the dominant most term?
Yeah, absolutely source resistance. Because
Uh,
here product we are multiplying product no, sir.
so this will be the dominant most term, right?
Yes, sir.
So it can be approximately written as GM R naught times RS,
Yes.
correct?
Hmm.
So so basically putting this particular transistor on top of RS increased the looking in impedance by a factor of how much?
1 by RS, sir.
No, no, not 1 by RS. It was already just RS. Okay.
Hmm.
Now
Uh,
you put this transistor on top of the RS. Your resistance became how much?
Means product of
It makes basically got multiplied by the self gain of the transistor.
yes, yes. Hmm.
Correct. So
Yes, sir.
this basically many a times this is used to increase the resistance. For example, let's say you have a current source. Okay, your current source will have some fine ideally what your current source impedance has to be
Infinity.
infinity, right? But
Hmm.
you make a practical current source. Let's say you are not getting infinity like a high enough output resistance from the current source. So there on top of that you can put this transistor, your resistance or output resistance of the current source uh, will be increased by self gain times. You understand?
Yes, sir. The
Okay.
so here in this case, RS value will depends, no, sir.
Yeah, it will depend on RS value. That's what I'm saying. If RS value is small and
Hmm.
you want to increase the value of RS, so what you will do is you will put an additional GMRO on top of RS, additional transconductor on top of RS, and that will basically enhance the value of RS by the factor of self gain.
Yes, sir. Sir, in Razavi sir will say by using the source regenerative that while in MOSFET in a saturation that while considering channel length modulation that slope will get decreased. No, sir. How it will decrease, sir, based on the source
I
resistance.
couldn't understand. Come again?
No, sir. While connecting the degenerative source resistance, if
Yeah.
MOSFET in saturation mode, considering channel length modulation, it won't be flat. No, sir. It will be slight deviation will be there, right? It move upwards. So because of degenerative resistance, that slope will get decreased. It will become mostly flat in non-ideal case.
I couldn't understand exactly what you want to ask.
No, sir. In MOSFET, while considering in saturation mode, we
Okay.
after overdrive voltage, it would be a flat. No, sir.
The ID versus ID versus VS characteristics.
Yes, sir.
Okay.
So if
So basically, you are saying, so let's say there was some VG over here. So this is this thing, and you are increasing the VD. Okay.
hmm,
And ID versus VD characteristic will be something like this,
in
but
ideal case, no.
but due to channel length modulation, it will be something like this.
Yes, sir.
Okay.
Yes, sir.
Now what?
No, while adding the source degenerator resistance, that slope will slightly reduce and behave like a ideal case, like that he explained, sir. But he didn't explain intuition behind how it will change.
So okay, we will try to find out the intuition behind this. So what is
Hmm.
the slope of this this particular? So in this case, So basically, we want to see how it becomes a good current source than the simple standalone transistor. What is the slope in this case?
Uh, Nothing but IDVD, no, sir.
Yeah, what is the slope? If let's say its output resistance of this particular transconductor is R naught, what is the slope?
Okay. Depends on lambda times of IDS, sir.
Yeah, yeah, yeah. So one by lambda ID is what?
Drain current equation only.
Okay, fine. Wait. So ID is basically in saturation half mu
Hmm.
n Cox W by L times VGS minus VT
Whole square.
whole
In
square
an
times 1
1 plus
plus lambda.
lambda
Yeah.
VDS. Yeah.
Okay. Now, basically, that is fine. Now, partial derivative of ID with respect of partial derivative of VDS, what you will get?
Yeah. 1 by lambda times of IDS. Yeah.
Lambda times, roughly lambda times ID.
Yes, sir.
Okay. Okay. So, this is, so 1 upon this is equal to, and what is this equal to? Roughly lambda times of ID, what is this equal to?
R not, no, sir.
1 by R naught.
Yes.
Okay. So the slope is equal to 1 by R naught.
Hmm.
You understand?
Yes, sir.
Now, basically, what is 1 by R naught? If let's say there was some VD, okay, there was some VD and on top of that you try to increase or decrease the VD, okay. If there is some output resistance over here, then what will happen if you increase the VD by, let's say, some delta VD, the current which was ideally supposed to be constant at some value ID now will be ID plus delta VD times R naught, correct?
Yes, sir.
Delta VD by R naught, sorry. So this is basically what is creating the slope in your slope in your this thing, your ID versus VD characteristic. You
Hmm.
understand?
Yes, sir.
Now,
Yeah.
now as we did this,
Incrementally.
yeah. Now as we did this question, there was this RS over here, there was R naught over here, GM over here, and you apply some bias voltage VG. Now what is so basically now let's say there was some ID, okay. There was some value of ID that was supposed to flow at some particular VD. Now
Hmm.
again, if you increase the VD at from that nominal voltage to some delta VD plus delta VD, how much increase will be there in the current?
Delta VD by R naught.
Delta VD times whatever output resistance that is seen from over here.
Yes, sir. Yes. R naught. Yeah. R naught plus RS 1 plus J.
R naught plus RS
RS GM times
yeah,
R naught RS.
R naught RS. This is basically this. So basically, this particular transistor now behaves as a cascode.
Hmm.
This
Yes, sir.
configuration is called cascode, and this is the output looking in output resistance of the cascode. This is a term that is an important term that you need to remember.
Hmm.
Okay. So now you can see, right? Earlier it was just 1 by R naught. Now it's basically, what is this roughly equal to?
GM
GM
times.
R naught times GM R naught, wait, GM RS times R naught. Okay. Now the slope will be, this will be roughly equal to ID plus delta VD upon GM RS times R naught. Initially, it was just R naught. Now it's GM. Now it's even more, the slope has now reduced. This you can see, right?
Uh,
Initially, it was what was it initially equal to? Delta VD by R naught.
Oh,
That
yes,
is
sir.
the incremental gain. Now it's delta VD divided by GMRS times R naught.
Ah, yes, sir. It is.
The
Yeah.
slope has reduced. Now, basically, this curve will look something like this, and the change in current due to change in VD will now be reduced many folds.
Yes, sir.
Understood?
Yes, sir. It's perfect.
Yeah,
Sir, one more thing, sir.
yeah.
Here that early voltage won't be will be considered, no, sir.
Sorry.
Early voltage.
Early voltage concept is not considered in MOSFET. That is a concept of that is a concept of what you call BJT. That is equivalent to channel length modulation in MOSFET.
Yes.
Yeah, so that basically early voltage. I don't exactly remember how that was the physical phenomena of that, but yeah, due to early voltage in active region. We call in BJT we call it active region. In active region where the IC versus VCE curve that was supposed to be flat in active region, that is not flat. That is slightly tilted upwards. Right.
Yes, sir. Same.
Yeah, so there that concept is called early voltage. Here there is no concept of early voltage. Here there is just channel and modulation and 1 by lambda ID.
Yes.
So basically, you got to know that the cascode basically helps you with what does it helps you with?
Sir, it will reduce the. It will increase the gain. At the same time, it will helps to make the constant curve. I mean, IDVD flat. I mean, there is
Correct.
no.
Basically, and IDVD flat meaning it will be behave like an ideal current source.
Yes, sir. Yes, sir. Exactly.
Okay, it won't be ideal, of course, but it will behave as a better current source, like than what you initially would have got with just simple one resistance. Okay, so let's say it basically can work like this also. Let's say, how does it increase the gain? You have V in over here with GM comma RO, and you have this thing V in over here. Here there is some biasing voltage. This is GM comma RO, and this is also GM comma RO. So what is the gain of the first circuit?
Yeah, sir. It should be minus GM or not, sir.
Minus GM R naught.
Hmm.
Okay, how do you calculate minus GM R naught?
uh, while considering eh, here MOSFET is one only, so input to output voltage, based on that we will calculate the transconductance or not across the drain terminal. Will in a small signal analysis, current source will be open circuit, and drain to source channel and R not will be parallel to the drain to source terminal. So based
Correct.
on that.
So basically, what you can say is so this is basically in small signal equivalent. It's basically like this. Okay. Uh, this is some GM. Uh, it produces a current of V in times dm, and this current downward current V in times dm, and this current goes into the output resistance of the circuit, that is ro, and your gain becomes minus gm times ro. Okay, now what happens in this circuit?
Here two circuits are known, no, sir. Transconductance will be if we take across in between
Okay,
uh,
so what do you define as a transconductance?
uh, GM, no, sir. I
Yeah,
mean, so
why
for
GM?
Means okay. Means it is the from input to the uh, from input to the output, or how much it is getting maximum flow, no, sir. If
Correct.
GM should,
Output. So basically, while finding the output, finding the transconductance, it basically, yes, like you give some input voltage and you check for the short circuit current at the output.
yes, sir.
Okay. So if you short circuit it over here, okay. So how much current will flow over here? What will be the short circuit current? It's basically kind of a Norton. You want to find it as a Norton equivalent of the circuit. What all things you have in Norton equivalent? You have a equivalent current source, equivalent Norton current source, and in
And
parallel to that you have
resistance.
Norton resistance.
Mm.
Okay. So what is the Norton? So short circuit current, or let's say the Norton current in on this particular branch.
GM into or not, sir.
No, not GM into R naught. GM into,
Circuit one on, sir.
sorry, circuit one. Yeah, correct. Circuit one.
Sir, GM into or not.
No, no, no. See, GM into R naught, is it a dimension of current? What is dimension of R naught? What is the unit of R naught?
Ohm, ohm.
And what is the unit of GM?
Okay. Yes, yes, sir. Yeah, reverse, reverse. Sir, it should be VN by or not, sir.
Where is R naught actually?
From it
Drain
should be
to
hmm, source.
source, right?
Yes.
Will there be any current flowing from in R naught? Will there be any current flowing in R naught?
It is grounded, no, sir.
Yeah, grounded on both terminals, right?
Yes, sir. No, sir.
So there won't be any current flowing into R naught. What will
No.
be the current flowing in the transistor?
Current flow is ISA only.
Yeah,
Applied
ISC.
current.
So what is ISC?
ISA is a VN by not getting, sir.
Veen. What will be the current? Okay, what is the current that will flow in this particular transistor?
Okay,
In
drain
small,
current only.
yeah,
Okay.
yeah. In small signal, what is that current?
Okay. GM into VN, sir.
GM into Veen. Okay.
Hmm.
So ISC is equal to, this is equal to
GM into VN.
GM into Veen.
Hmm.
What is the Norton resistance or the output resistance?
Or not.
R naught. Okay. So basically, this behaves as a current source of
GM VN in parallel with R not.
GM Veen in parallel with R naught. Correct.
Yes, sir.
What is the voltage that is developed at this node then?
At load GM into VN by R not into R
Minus
not.
GM into Vn into R naught.
Yes,
Right.
sir. Yes, sir.
Okay. So this you have. Okay.
Hmm.
Now let's come to the second circuit. Let's try to apply the same principle over here. What is the short circuit current now?
Yeah, it is the current flow from MOSFET 2 and 1, sir.
this is MOSFET 2. Let's say this is MOSFET 1. So
Yes, sir.
in small signal analysis, VB. Just a minute.
Yes.
1 second. Okay. Can you hear me? Hello. I am audible. Hello. Thalpasai, can you hear me? Okay. We were discussing what is the gain in this particular circuit. Okay. So let's say, so what is the short circuit current in this? Now, in case of when the biasing voltage VB, so this is basically biasing voltage. So in small signal analysis, this particular terminal will become ground. So we will have over here as ISC. The current source, of course, will become open circuit. Okay. So this will be our signal. This will be our circuit when we need to find out small signal analysis. Okay. So at this particular node, the current that will be flowing from the input transistor, that is the transistor 1, will be equal to gm times v in again. Okay. Now this gm times v in will can either flow in this direction or this direction. Correct. So let's see. Looking in impedance at this direction is R naught, and looking in impedance in the upper direction. So let's see what is the looking in impedance in the upper direction. This is basically equal to. This is almost equal to 1 by gm. Correct.
Yes, sir. While looking at the source.
Yeah. In which direction most of the current gm times v in will flow?
Sir, it will flow. It will flow to both.
So
Like it will divide, no, sir.
yeah, but where will the majority of current divide? One side it's 1 by gm, other side it's r naught.
Yeah, it will divide by 1 by gm. Then 1 by gm is very small. No?
1 by gm is very small as compared to r naught, so we can assume that almost all the current, if gm ro is much greater than 1, then almost all the current will flow inside 1 by gm. Correct.
Mm-hmm.
Okay. So if that is the case, then ISC is again equal to.
Sorry, sir.
If let's say most of the current will flow into this particular transistor, then
Yes, sir.
ISC that we are calculating is equal to.
Yeah, it should be minus gm times R naught.
No. It's again ISC, the short circuit current.
Oh, okay. Yeah, it should be GM times of R naught, no, sir. GM into VN.
Again,
Yeah,
what is the GM times?
yeah, GM times VN times R naught, sir.
No, no, current. I'm talking about the current, the short circuit current. It's basically GM times V in current was flowing over here.
Mm.
The same current will flow from here, right? It will be GM times V in. You understand?
Yes, sir.
Yeah. So ISC will be equal to GM times V in again. Do you
Okay,
get?
sir. Yes, sir. Yes, sir.
Okay. So ISC is equal to GM times V in, and what will be now the Norton resistance then? RO. This is GM. This is RO, and this is grounded. And you are to look in the Norton see the looking in impedance from this particular the drain of the cascode transistor, the upper transistor.
Yes, sir. It
Okay.
should be GM times R0 square plus R0 plus R0, sir.
GM times R0 square plus R0 plus R0, which is roughly equal to GM times R0 square.
Yes, sir.
Okay, so your gain is now so it basically looks like GM V in parallel to GM times R0 squared. Correct?
Yes, sir.
Okay. So it's basically so output voltage here now is equal to minus of
GM VN, yeah, GM square.
GM square
R naught square into VN.
R naught square into V in. So
Mm.
you see the gain over here was just GM RO, and gain at this node is GM square RO square. Okay.
Mm.
So your gain has basically the gain on applying two identical transistors in cascode, your gain has increased by a factor of GMR. Okay, so basically a cascode can be used to increase the gain of the common source amplifier. You understand?
Yes, sir. Yes, sir. Cascade, and after going multiple triples, I mean, telescopic will face uh, output swing issues
Yeah.
like that.
Correct.
They meant.
So basically, you need some amount of headroom for each transistor to behave in to be in saturation, and if let's say you don't have enough this thing for the transistors to be in saturation, then you will then so basically if you keep on stacking transistors in one on top of each other, you will face the problem of the transistor not having enough space to remain in saturation. So these all equations are valid only if the transistors are in saturation. If they go in triode, then these equations are not valid.
Mm.
Okay. Now let's come to another question. So this question basically over here, this is the problem 2 of. So you need to find the gain from input to the output. Okay.
Yes, sir.
How will you proceed?
Yeah. First, I mean, we can make it de-energize.
What will you de-energize?
VB we can de-energize, sir. VB we can make it ground gate voltage,
VB will be
and
ground.
yeah, source voltage will be there. VN.
Source voltage will be there.
Mm.
Vin
And
will be there.
mm. and RF is connected between a source and a drain. And RD is parallel to RD is grounded, sir. one terminal is connected to drain, one terminal is grounded.
Correct. And where are you taking the output?
Yeah, across the drain terminal, RF. Yeah.
This is output.
Yes.
Correct.
Mm.
Now, okay. So let's try to write the current equations over here. What will be the current? What will be the current that will be going into the transistor?
Yeah, VN by RF set.
Sorry, come again. V in by?
Sir, VN
Okay,
RF.
let's divide the current that will go in two directions. Okay, there will be some current that will be going into the transistor. Let's call it IT, and some current that will be going into the RF resistor. Let's call this IRF. Okay, what is the value of IT?
Yes, sir.
The
Oh,
transconductance of this
yeah, GMVN, yes.
GMV
No, G minus, yes, sir. GMVN, correct.
in. Okay, what is the
Yes,
value
sir.
of IRF?
VN by RF. Oh, VN minus V out by RF, sir.
V in minus V out by
V out by RF.
RF. Okay. So your overall current that goes over here is basically IT plus RF, right?
Yes, sir.
GM
GMVN, VN.
plus V in minus V out by RF. Now,
Equal
what is V out now? So the same current, same particular current can be written as what
only
will be the
V.
current flowing through RD?
Yeah, it should be V out by RD, no, sir.
V out by RD, and this is equal to
Yeah, GMVN minus V out by RF.
correct. This is equal to V out by RD, correct?
Yes, sir.
You understand?
We can take a common V out common.
Okay, so basically, what is V out? V out is equal to
Yeah,
M
GMVN.
plus 1 by RF times V
Yes,
in,
sir.
and over here, what will come?
1 by RF plus RD, sir. Yeah,
RD
yeah.
plus RF upon RF RD, correct?
Yes, sir.
So V out by V in is equal to GMRF plus 1 upon RD plus RF times RD, right? This is basically your V out by V in, correct?
Yes, sir.
Now, tell me what will be the looking in resistance from this node, R out. You know the V out now. What is the value of V out?
Yes, sir. V out is down. We are. Sir, I mean, I didn't write down the questions.
So V out is basically equal to, I will copy this over here.
Yes, GMRF plus 1 RD plus RF.
So V out is equal to GMRF plus 1 upon RD plus RF times RD times V.
Yes, sir.
Correct? So what
Yes,
is now, can you tell me quickly what is the looking in impedance from this node, the source node?
Impedance. Okay.
How will you calculate it? If there is V in voltage over here, what will be the output resistance? V in by,
VN by test voltage we can apply, no sir. VN by.
yeah, let's say you test voltage is V in only. So V in by whatever current is flowing inside that is equal to your output resistance, correct?
Yes, sir.
Now, what is the current that is flowing in?
Yeah, IT plus RF, no sir.
Yeah, what is that? You know the output voltage over here. Okay.
Hmm.
So what is the current that is flowing through RD?
Hmm.
Sorry, this is ulta. So what is the current that is flowing through RD now? You know the V out. What is the current?
Yes, sir. V out by RD, no sir.
V out by RD. So what is it? Can you tell from this equation?
Yes, sir. RD plus RF divided by GM RF plus 1.
Okay.
Hmm.
Now this is the same current that goes from the input side also, right?
Yes, sir.
This times V in. Okay.
Hmm.
Wait. Yeah, correct. So this is the same current that goes from the input terminal also, right?
Yes, sir.
Okay. So you know your I in has the value of, what is it?
RT
Uh,
plus RF.
wait. It seems a little off over here. There is. Mm, wait a second. There is some glitch in the formula. RD will come over here, right? Mm, RD will be at the top. GM RF plus 1 divided by RF plus RD. GM RF plus 1 divided by RF plus RD. So your current will be GM RF plus 1 divided by RF plus RD. This will be your current. So IN is equal to GM RF plus 1 divided by RF plus RD times VIN. Correct?
Yes, sir.
So your R, this is not R out, this is RN. So RN is equal to RF plus RD upon GMRF plus 1. Okay. Now, how do you know this is correct?
Sir, by dimensions we can correct, no sir.
Okay,
J.
dimensions is one thing.
Hmm.
Okay, how with dimensions it's correct?
Yeah, here RF ohms and GM is 1 by inverse of ohm will
Correct.
get cancelled. It should be one constant value plus 1, and RF is ohm, so Rn is ohm, so it becomes
Okay.
like that.
Other thing. Okay, let's try to see make sense from the circuit also. So let's say this transistor was not there. Let's say this transistor was not there. That means GM was equal to 0.
Hmm.
So how would the circuit look? If GM was equal to 0, the circuit would have looked like there would be
RF
RF,
plus R.
there would be V in, and there would be one RD over here. Okay. So what would have been your RN?
Yes, sir. RF plus RD by.
RF RD.
Hmm.
So can you see from this equation? It's the same thing, right?
Yes, sir. Yes, sir. Series.
Okay. If GM goes to 0, you just have RF plus RD. So
Hmm.
GM equal to 0 makes sense. What if RF equal to 0? How will your circuit look?
Yeah, RF equal to 0 means it should be. Yeah, RD is common source, sir. Yeah, not common source. Drain resistance will be there.
So what is the looking in impedance from here?
Yeah, RF, RD, sir.
Sorry, come again.
RD, sir.
Uh, this was sorry. What? Not RF equal to 0. RF equal to infinite.
Hmm. Right. That's one. Sir, 1 by GM, sir.
1 by GM, correct?
Yes.
So from the equation also, if you put as RD infinite, upper and lower basically put the limit RF equal to infinite, you will get Rn equal to 1 by GM.
Hmm.
Okay, so you know that the equation that you have is correct. So you found out the voltage gain from input to output, and uh, basically the input resistance for this particular circuit. Let's move on to the other circuit. Let's try in this circuit. So again, we'll draw the small signal equivalent V in. We have RF over here. Then we have RS.
GM. GM1 VG minus
GM
VS.
times GM1.
Hmm. VN minus VS.
What is VS?
VS is GM1. Okay.
From this circuit, what is VS?
V out by RS, sir.
No, no. What is
No.
VS?
Okay, sir. VS. Yep.
It's simply V out, right?
Yes, sir.
The source voltage is only V out.
Hmm.
So this is equal to V out. So what is the current that is flowing in this direction? GM1 times
VN minus V out, sir.
V in minus V out.
Hmm.
Okay. So now what will be your this thing? So what will be the current that will be flowing in your RS?
Yes, sir.
One will be this current, other will be this current.
This. Yes, sir.
Okay. What is the total?
Yeah, GM1 VN minus V out.
GM1 V in minus V out.
Yeah, VN minus V out by RF.
V in minus V out by
RF equal to V out by RF.
V out by
RS, sir.
V out by RS.
Mm.
Correct.
Mm. Sir,
So
GM1 plus RF plus 1 by RS V out.
we'll take all the V in terms on one side. It will
Yes, sir.
be GM1 plus 1 by RF,
Yes, 1 by
and
RF.
V out terms on other side.
Mm. GM1 GM1 1 by RF plus 1 by RS.
1 plus 1 by RF plus
Mm.
1 by RS.
RS.
So your input to output equation is V in by V out is equal to
Yes.
GM1, let's call it RF parallel RS, plus 1 divided by
GM1 plus RF.
and over here you have RF by RF parallel RS. So if we try to simplify it a little bit, we get RF RS upon let it be RF parallel RS over here. Plus, sorry, GM1 RF plus 1 plus RS upon RF. No, RS. Correct?
Yes, sir.
Okay.
Yes, sir. RF get cancelled.
Yeah. Are you sure this is the correct equation? Let's say your RF is equal to infinite. What will happen? You have, let's say RF is equal to infinite. You have
GM.
On top, it will just be RS plus 1 divided by
Yeah, sir. It should be RF, no, or yeah, GM, sir.
GM1 times RS. Correct?
Yes, sir.
There seems some, it seems ulta. It doesn't seems this thing. Just a minute. Yeah, correct. It's opposite. It's opposite of this. I'm sorry. See, over here, you have V out by V in, right? So it will be GMRF. Wait. GMRF plus 1 divided by, this will be opposite of reciprocal of this. So your value is this is equal to GM1 RF plus 1 divided by GM1 RF parallel RS plus 1 times RS upon RF plus RS. What happens if GM is equal to 0?
Sir, RS plus RF plus RS, sir.
Sorry?
RS plus RF plus RS.
RS by RF plus RS. Does this make sense? So if GM is equal to 0 in this particular case, there will just be a voltage divider between RF and RS, right?
Yes, sir. Correct.
Okay.
Yeah, dimensions also correct. Yeah, correct.
Yeah. So this equation is now correct. Now, let's say you need to find the looking in impedance from over here. Okay. And the other thing that I tell you is your GM is infinite. Can you quickly tell what will be the looking in impedance based on what we discussed on Friday? What did we discuss on Friday for GM for the circuits where we have current control?
Yes, sir. Yeah, we will get a inverting a negative feedback. R minus RF.
What particularly will provide you negative feedback over here?
GM tends to infinity, we can get a negative feedback. As GM
Yeah.
tends to.
So can we check whether this circuit is in negative feedback or not? How does the circuit looks? It basically has VDD at the top. For checking the negative feedback, you can basically de-energize this input. This is RS. Sorry, this is RF, and this is RS. Okay. Now, let's say this voltage wants to go up. What will happen? If let's say this is VS, this wants to go up. What will happen to VGS?
Yeah, sir. VGS will get reduced, no, sir.
That means VGS will reduce.
Hmm.
What will happen to the current?
Yeah, current will also reduce because it is
Current
related to the.
current will
Hmm.
reduce. So
Hmm.
the current that is flowing like this has reduced. So what
Hmm.
will happen to VS now?
Yeah, VS will also reduce, sir.
VS will also be reduced.
Hmm.
So if VS was trying to go up,
Hmm.
the transistor is trying to bring back the VS to
Hmm.
its original position. Okay,
Hmm. Yeah,
it's trying
negative
to
feedback.
reduce the VS. So the
Hmm.
circuit is in negative feedback. Now,
Hmm.
now we know that the circuit is in negative feedback. This is V in, and we need to find out R in when GM tends to infinity. Okay, there is RF over here, there is RS over here, and here is V out. So you have V in over here and V out over here. If GM tends to infinity, what will happen to the controlling voltage? And this circuit is in negative feedback. What will happen to the controlling voltage?
Controlling V out, no, sir.
What is the controlling voltage in this case? For the what?
Oh, VS. Yes, V out, V out, V out.
Why only
So
V out?
because it will if it is increasing, no, sir. So get to source voltage is getting reduced.
Yeah,
So that,
but,
based on that,
V naught
drain
is
current.
there. So basically, what controls the current in the transistor?
VGS
V
only, no,
minus
sir.
V out, right?
Hmm?
VGS is V in minus V out, right?
Yes, sir.
Yeah. So if the controlling voltage is V in minus V out, okay.
Hmm.
Now you tell me what will happen to the controlling voltage if the GM is infinite.
JM is infinite, and then it should be VN is equal to V out, sir.
V in is equal to V out.
Hmm.
Okay. So if V in is equal to V out, will there be any current that will be flowing through RF?
No, zero.
I is equal to 0. There won't be any current flowing into the gate of the transistor as well. Correct?
Yes, sir.
So what will be the R in?
Infinity.
Infinity. So you can quickly get the value of Rin if you know this trick. Otherwise, what you would have done is you would have found out the looking in impedance in terms of RF and then put the limit as RF tending to infinity and then would have found the input impedance. But if you know this technique, it will save you so much of algebra.
Hmm.
Do you understand?
Yes, sir. Yes, sir.
Okay. So next question is this. Again, so let's say M1 and M2 both have GM comma R out and GM comma R out. Okay. So this is question number 3. No, question number 4, right? This was 3. This is question number 4. So now let's now try to we'll try to write the small signal equivalent. First of all, we'll try to write the small signal equivalent for M1. So we have Vin at the gate of the transistor. And then there is this GM times. Let's call this voltage is V out. GM times
V minus V out.
V out. And we have output resistance of R naught.
R01.
Correct.
Yes, sir.
And here it is grounded. So, and the small signal equivalent of M2, how will we write this?
Yes, sir. Here it is. Vn is grounded, and source is grounded. So GM V out minus. Sorry. Yeah, it should be.
Will there
Vn.
be any GM over here?
No, sir. R02.
That just will be R0. Let's call it R0 only. Okay. So it's basically like you guys have done common drain configuration.
Yes, sir. There should be no voltage drop across the R0 parallel with R0. Yeah.
And there will be RO by 2. Correct. So what will be output voltage over here now?
Output voltage.
V out by RO by 2 is equal to GM times
Vn minus V out.
V in minus V out. So if you calculate V out by V in, that comes out to be GMRO by 2 divided by 1 plus GMRO by 2. If GM tends to infinity, V out equal to V in. Do you understand this?
Yes, sir.
Okay. Again, same principle can be applied over here. Which transistor is in negative feedback? Can you tell?
Sir, down, sir.
The down one is negative feedback. Why?
Screen down, sir. Full. Yes.
Yeah.
Yeah, fine.
So out of M1 and M2, which transistor will be negative feedback? Let's say the output voltage tries to increase.
Yeah, sir. M1, sir. M1, sir.
Okay. Why?
Yeah,
If
if
the
V out.
try to explain me the complete flow, how will you check that?
Yeah, sir. If V out is increasing, no, sir.
Okay.
So then then current will get reduced.
Due to which transistor? M1 or M2?
M1, if V out, we are seeing small signal only, sir. So M2 will doesn't come into picture now.
Why?
Because
M1 has okay.
M2.
If what will happen due to M2 and what will happen due to M1?
Sir, if V out increases, sir, if V out increases, then current will get reduced, no, sir.
Why? That's what I'm asking.
Here, GM V in minus V out is there, no, sir. V out is the source voltage of M1, right?
Correct. So
So
due to this current, that is GM V in minus V out will get reduced. Correct.
yes, sir.
But I will say that okay, here there is output resistance R naught, right? So V out by R naught will increase.
Okay. Okay. Yes, sir. Sorry, M2. Yeah. Sir, my intuition is here here M2 will act as source resistance, sir, R0. So if Vs is getting reduced, no, sir.
Yeah.
Hello.
Yeah.
Yeah. If
No, no. Okay. M2 will act as source resistance. Fine. Okay.
mm, mm. If source resistance is getting reduced, means if source V out is coming reduced, if it is coming to increase means then VGS will means Vn minus V out will get reduced. So ID will reduce. So a negative feedback is M2 will play a major role based on the source resistance.
No, no, no. Come again. No, come again.
Yes,
If
sir.
yeah, what is there like due to like will there be any GM due to M2?
No, but output resistance is there, no, sir, R0.
Output resistance is there. Okay.
Mm.
So let's come to this particular circuit only. So if V out is trying to increase,
Mm.
what will happen to V out by R naught?
Yeah, V out by R naught will increase means V out by R naught will decrease, no, sir.
V out by R naught will,
Decrease
why V out by R naught will decrease?
means output voltage is getting increase means current will get decrease, no, sir. Oh, no, no.
No, output voltage is increasing if V out by R naught. Okay. If
Mm.
V out is increasing, V out by R naught will also increase, right?
Yes, sir. Yes, sir.
Okay.
Okay. Mm.
So this current is increasing, the upper current is reducing. What does this
Mm.
mean?
Okay, okay. We are stable increasing. Yeah. So V out is the negative. I mean,
Okay, is there any controlling terminal for M2? You tell me this.
controlling terminal M2 is nothing but V out only, no, sir.
Okay, so there is some amount of V out that is increasing over here, some amount of current that is increasing over here. What will this increasing current do?
Yeah, it will increasing the current will flow to, okay. Increasing current is there, then we there will be decrement current across from
No,
the
you so basically see it this way.
mm,
Let's say the upper transistor was not there. Okay,
mm,
it
mm,
was just R naught,
okay.
and here was V naught. Okay,
Mm.
if I try to increase the V naught, will there be will this R naught try to pull back V naught? It won't, right?
No, no, it
It's
won't.
just a passive resistor. There is nothing active element. There is no active element in this for M2. It's just a resistance.
Yes, sir.
Okay, so M2 will not play a role in negative feedback. It will be the M1 that will be playing the role in negative feedback.
Exactly. Mm.
Okay, so M1 will play the role in negative feedback. Okay, so if GM of M1 tends to infinity, what will happen?
Uh, okay, GM M1 tends to infinity. Okay, it should be okay. Simply R0 I in R01 plus R02, sir.
Sorry.
Sorry, it should be parallel of two output resistance R01 and R02.
No, no, no. Your V into V out, what will be the gain?
Oh, gain, sir. Okay, okay. Should be, yeah, it should be minus GM1, sir, into output
So if
resistance.
GM tends to infinity, we discussed that due to M1, your transistor is in, the circuit is in negative feedback. Okay.
Mm, mm.
So what will happen to the gain of the circuit?
Yeah, it would be negative feedback only, sir. I mean, it would be inverted output.
Uh, Sorry.
Yes, sir. Output would be one, sir. R0 here. Uh, feedback resistance by, okay. Here feedback resistance is R0. Sir, 1, sir.
Why one?
Here, I mean, for M1 and M2, R naught is same, no, sir.
Okay.
So if a GM tends to infinity, then in small signal infinity means there should be no current flow of from input
It's
resistance.
no, if a GM is infinity, what
Mm,
we discussed is the controlling terminal will go to the controlling terminal, the controlling parameter will become zero, right?
mm, mm.
So,
We
what
have to
is the
see.
controlling parameter?
We out, sir.
Controlling parameter, no, no, no. Why V out? Controlling parameter for M1. M1 is a negative feedback, right? We discussed.
Yes, sir. M1 is negative feedback. How can we? Okay.
The current, in M1, we have the current flowing is GM times V in minus V out, right?
Yes, sir. Mm.
Okay. So, V in, it will be V in minus V out times GM. And I am
Mm.
saying GM is going to infinity. The transistor M1 is a negative feedback. So, so V in minus V out shall go to zero, right?
Mm, mm.
And if V in minus V out is going to zero, basically V in is equal to V out. The gain is 1. This is again
Yes,
a
sir.
source follower. So it's similar to the previous problem. Let's say if RF was not there and there is some RS. So instead of RS over here, we have the output resistance of the transistor M2.
Exactly, sir. Mm.
Okay. So here also the gain is equal to 1. Now the last question, you need to find out Ix by Vx. This you can find out quickly.
Yes, sir. Here both there is no AC, no, sir. Okay.
Let's say this is AC. Okay.
Mm.
What is the looking in impedance on top?
Yeah, 1 by GM, sir. 1 by
1 by.
GM1.
What is the looking in impedance in the bottom?
Bottom. Yeah, yes, sir. Considering channel and modulation, sir.
Yeah, yeah.
Okay. Yeah, it should be R01, R02.
R02, and there will be one looking in impedance due to R01 also, right?
Yes, sir.
Okay, so can you quickly tell what is the overall now Ix is equal to Vx by the resistance that is looking in over here. What is it
Mm.
now?
It is parallel
1 by
R0.
M1 parallel R01 parallel R02.
Yes, yes, sir.
Okay.
Mm.
So this is just the gain of that. You can simplify it and get the exact this thing. Exact will come out as uh, GM1 parallel GM1 times R01 parallel R02 plus 1 divided by R01 parallel R02. Okay. So
Yes.
any other doubt?
Sir, sir, I mean, for cascading in week 3, small doubt on problem 2, sir. You could you intuition, sir. I mean, way to solve, way
Which
to
one?
approach it, way to approach, sir.
Which problem?
Problem 2, sir. I think problem 2.
Can you share your screen and present that problem once?
Yes, sir.
The problem two is which one? This is the second figure that you are talking about, right?
Yeah, sir, this one.
So it's basically
Here, I mean, current 100 microamperes, it correct will replicate to C2, no, sir.
100 microampere current will replicate to both of the transistors. There are two stages over here basically.
Mm.
Okay, there are two stages. Basically, the way to solve this problem, first of all, you just do the large signal analysis.
Mm.
Large signal analysis you do, you will get the GMs of the relevant transistors, GMs and output resistances of the relevant transistors. And
Mm.
once you get that, then you short all the these C1, C2, C3, all these capacitances.
Mm.
So after that, you will just get a cascade of a common source amplifier followed by a common drain amplifier. Can you see this?
Which one? This one, sir. Mm.
Which so the
Yes, this one. Yeah.
what is this one?
Yeah, common drain here.
A common drain. And before that, what is it?
Yes, common sources.
Which one?
Here it is shorted, no, sir. Here it is. Yeah, the both are common drain ones.
No, no, no. This the lower transistor is just a current source. It doesn't has the input in it, right?
Okay, here 100. Yeah.
It is just a current source that will provide you with 1,000 microampere of current.
Okay, lower transistor. This one also.
Yeah.
Okay. So the same current will get flow here.
No, no. What I'm saying is,
Mm.
you find the current in all the branches. You
Mm.
calculate the transconductors of the relevant transistors, and then
Mm.
you just apply the small signal analysis. In small signal analysis, you will have a common source followed by common drain.
Mm.
Now you told okay, the output transistor is a common drain transistor, which is the common source.
This one. Yes.
Which one?
Sir, this one is a common source, no, sir. Common source.
And common source, where do you is there input going to the gate of this transistor, the lower transistor? Where is the input?
Sorry, 100 microamperes is coming here.
No, no, you
Lower.
need to find V out by Vi, right?
Yes, sir. V out by here from here to here.
Okay, so is there input going to the gate of that particular transistor?
Sir, I mean, could you please write down, sir, this?
Okay, just a minute.
Yes.
I'll give you a small hint in this. I
Yes,
won't
sir.
say the complete.
Yes, sir.
Can you see my screen?
Yes, sir.
Okay. So this you said is a common drain transistor. Why?
Mm.
Your drain is connected over here. The
Mm.
input comes from here and output goes over here.
Mm.
Okay. Similarly, this place, if you see, your C2 will get shorted, right? In small signal.
Yes, sir.
If your C2 is shorted, what will happen is your input comes from here, your output goes at the drain. So
Mm.
what is this? And your source is shorted. What
Yes,
is it?
common source. Yes,
Common
sir.
source. Okay.
Yes,
So
yes.
there is a common source stage followed by a common drain stage. Now you can find out the gain from input to output. You just need to you can individually find out the gain of the common source. You can individually find out the gain of the common drain. And since these two are in cascade with each other, you can multiply it and get the answer.
Yes, sir. Here it is a not cascade. Yeah, cascade. Both complications are there, no, sir.
No, where is cascode?
Okay. Yeah, there is no cascode. Yes, only cascade.
Cascode happens when there is a transistor above the so okay, there is cascode for this transistor, let's say, but
Hmm.
that does not matters that does not matters at all. Why? Because this is anyways going to get shorted. Other
Hmm.
thing is okay, yeah, this will get shorted in small signal, it doesn't matters at all. Had the cascode this transistor there would have been a transistor above the input transistor, then you will say that this is a cascade this is a cascode. But
Yes, sir.
in the current condition there is no cascode.
Yes, sir. Perfect.
Understood?
Yes, sir. Yes, sir. Getting.
Okay, any other doubt?
No, sir. Perfect. Yeah.
Okay, then if there is no doubt, we can close the session now. Thank you for attending.
Yes, sir. Thank you. Thank you very much.